Um, cool. All right. Well, my name's Robert. I'm from the Filecoin Foundation. I'm a developer advocate engineer. I'm here today to tell you a little bit about the Filecoin tech stack, but I'm also going to preface it with some information about Bitcoin and Ethereum, if that's all right with all of you. Okay. And by the way, I do know that I'm the one standing between you guys and dinner, so I will try to be shorter than an hour. And hopefully we can make it a half hour, but we shall see. All right. This is the Moore School of Electrical Engineering at the University of Pennsylvania. And it was here in the 1940s that researchers from the Army, the Navy, Harvard, and Penn came together to develop something called the ENIAC, which was the first general-purpose Turing-complete computer. This ENIAC was made of these kind of light bulb looking things. They're called vacuum tubes. And effectively, with a vacuum tube, when you have electricity flowing through them, you have a 1. And when you have no electricity flowing through them, you have a 0. And that gives you your binary mathematics in order to do all the computation that makes up that computer. Now, as you saw, those vacuum tubes are very large. And it was not until 1959 that Caltech professor Richard Feynman made a talk called Plenty of Room at the Bottom, the transcript of which is published online. I encourage you to read it. But he theorized that and said, hey, listen, we are currently in a space race. We're building huge things. We're going to the moon. What if we built small things? I'm talking about an automobile smaller than the dot on this page. I'm talking about writing the entire Encyclopedia Britannica on the tip of a pin. And so he put out 12 challenges, and many of those challenges were accomplished. But this really gave rise to the age of silicon. And people began using silicon to manufacture very, very, very small things that make up our computing world today. And the specific device that is really the heart of all of our computers is the transistor. So this is more or less a voltage gate built into silicon that you can control whether or not electricity flows across the gate. And if there is electricity flowing across the gate, you have a 1. If there isn't electricity, you have a 0. Just like the vacuum tube, except this is significantly smaller. It's so small now that you could fit 2 billion of them on the size of a 2-inch by 2-inch chip. And that's when I made this deck about a year ago. So it's only gotten smaller and more impressive. And I believe some of these now are the size of a few atoms, which is really, really crazy to think about. But this was made possible thanks to silicon being a semiconductor. Semiconductors can both conduct and insulate electricity. So this is Moore's law. This is a trajectory of electricity. So this is Moore's law. This is a trajectory of how many of these transistors you could fit on a 2-inch by 2-inch chip. And people theorize that we'd hit a limit at the top someplace, but we'll probably have a new Moore's law as we get to the atomic scale transistors. And this is a 4-inch by 4-inch wafer showing probably 100 chips, each with 2 billion transistors on it. Now, if you were to take the computing power you have in your phone, in your pocket, right now today, and you built a computer with that computing power, but out of vacuum tubes, you would need the physical space of the entire Pentagon building in Washington, D.C. in order to be able to achieve that. So I just wanted to highlight what a miracle it is we have in our pockets and what technology has graced us with. Naturally, once we have all these devices, in comes the internet. And with the internet, we have naturally these devices sharing information. And there's a specific group from the internet I want to highlight. These are the cypherpunks from the late 90s. Who were the cypherpunks? Well, this was a mailing list. And these were engineers and activists who cared a lot about privacy technology. And in their mailing list, they wrote all sorts of things about why privacy on the internet is important. And in fact, many of these cypherpunks were actually involved in the earliest conversations on the Bitcoin Talk forums, with Satoshi helping influence the design of Bitcoin. One such cypherpunk was named Hal Finney. Hal Finney received the first Bitcoin payment from Satoshi. Now Hal Finney unfortunately suffered from ALS, so I don't know whether his family had him cryogenically frozen, but he's no longer with us. But nonetheless, this group was very important to the philosophy of Bitcoin today. And naturally, a decade later, we have the financial crisis, and this Times article referencing a bailout for the banks during the 2008-2009 financial crisis is referenced in the Genesis block of Bitcoin. Now, let's talk a little bit about Bitcoin before we get into Filecoin. Bitcoin introduced a number of very interesting technological advancements. The first of which is a new privacy model for financial accounts. So instead of the counterparty and the trusted third party knowing who you are behind a wall and the public not knowing at all who you are, naturally with Bitcoin wallets, the public can see all transactions, but these transactions are done with anonymous wallet addresses, and the identity of that Bitcoin user is anonymous or pseudonymous. Now, we're going to see in a minute using with Ethereum and smart contracts and tracing these transactions, how we might reveal something about these anonymous addresses, but we'll come back to that. There are thousands of miners all over the world competing to mine blocks on Bitcoin. What does that mean? Well, first of all, who could tell me what an actual block in Bitcoin is? Sorry? I'm sorry?
85,000. The number flow you requested.
Yes, but I mean, in like on your computer, what is what is a block?
It's a chunk of transactions.
I'm sorry?
A chunk of transactions.
It's a bit of memory, and in that memory, the miners are competing to add transactions from the mempool. That mempool is the purgatory waiting room of all the transactions from all the Bitcoin users that want to conduct a transaction. The miner will then label the block with the highest number +1, and they will reference the previous block, officially chaining. That's where maybe the part of the name blockchain comes from. But they will reference the previous block, and then they will solve something called a nonce. So that nonce is a difficult cryptographic puzzle. Practically, the Bitcoin miner is generating many random numbers, and they're guessing at what the solution to that cryptographic puzzle is, and they're going to keep guessing until they get it, and once they get it, they propose this block with the transactions and the solution to the rest of the Bitcoin miners that are mining Bitcoin. So when that happens, if all the other nodes say, hey, this proof of work looks good, and hey, these transactions look legitimate, we accept this block and we're going to start building the next blocks, referencing this one as the previous one. Now, I said two important things. One was they're checking the transactions. And Satoshi in the white paper actually gives a formal definition of what Bitcoin is. Does anyone know what that formal definition is? An actual quote from Satoshi.
A decentralized electronic peer-to-peer cash system, I think.
That is the subtitle of the paper, and it is correct, but it is not the formal definition referenced in the paper. Anyone else want to take a guess?
It's like a DLT, maybe?
That is also describes Bitcoin, but is not the for the formal definition of what an actual Bitcoin, like a financial, like the actual Bitcoin is. Anyone else want to take a guess? Okay, I'll just tell you. A Bitcoin, according to Satoshi, is a chain of digital signatures. What does that mean? Well, any Bitcoin you receive is actually the actual data that's associated with that Bitcoin are all of the private keys from the wallets that have signed for that Bitcoin in transactions before you receive that Bitcoin all the way up to when you received it. So everyone who has previously owned that amount of Bitcoin that you received in the past and has signed and sent it, that Bitcoin is the chain of digital signatures. And what the miners are doing when they're checking transactions is they're making sure that this chain of digital signatures is legitimate and that that Bitcoin hasn't been something called double spent, meaning one actor tries to send the same Bitcoin to two different people in the same block. Does that make sense? Cool. Okay, so that's the first thing the miners do. I'm going to skip that slide. And then the second thing they do is they check the nonce to make sure it's correct. And if the block is accepted, well, they get paid some newly minted Bitcoin that's never been in circulation before. And this is my favorite chart probably in all of technology. This is the Bitcoin controlled supply chart. Many of you probably know it's the Bitcoin halving today, yesterday, tomorrow, who knows? Tonight.
Yeah.
Great.
11:30.
Yes. Yeah. So what this means is that the amount of Bitcoin that a miner is going to receive for the same amount of electricity they're going to spend, or the amount of Bitcoin that they will receive for mining a single block, is going to cut in half. And the result of this phenomena, this miner's reward is the blue. So it started at 50, went to 25, went to 12 and a quarter, etc. The result of that phenomena is a very interesting controlled supply, money supply of the Bitcoin, and that's this red line here. So you have scarcity. You only ever have 21 million Bitcoin. Okay. This is a graph, and I am realizing I should use a different graph. But this is a graph comparing the central bank independence against inflation rates. So as you can see, the more independent a central bank is, the lower the inflation rate, but it always seems to be positive. And the reason for this is when governments have more control over their money supply, they like to spend money now on debt, then print money and pay everything back with devalued currency later. So you see real crisis levels of this in places like Zimbabwe, Venezuela, other countries, but nonetheless, Bitcoin, the financial aspect of Bitcoin is meant to be an answer to this. Okay. Cool. Please excuse me. I've had a bit of a rough week. So, okay. I'm going to skip that slide. All right. Enter Ethereum with Vitalik saying, hey, not only can we do transactions like on Bitcoin, we should also be able to do any type of commerce. And when we do commerce, what is it that defines our relationships? Well, it's contracts. And so enter Ethereum, which is a blockchain with smart contracts on top of it. Naturally, you guys all know this. But what's interesting is that if you look and compare the original design of Ethereum compared to Bitcoin, there are very specific design choices that are made to enable Ethereum as kind of a place for global commerce. First of all, the block time is significantly faster. Bitcoin 10 minutes, Ethereum 10 seconds. The block size is much smaller, anticipating that there will be fewer but more rapid transactions happening in each specific block. The miner's reward is fixed. There's no half-life. That's a discussion maybe for later. And naturally, Ethereum has moved to something called proof of stake. Now, there's something specific I also want to tell you about that is often ignored, and that is, that is the difference between accounts on Bitcoin and Ethereum. On Bitcoin, we have a system called unspent transaction output. Who here has heard of this before? Perfect, a few of us. So unspent transaction output works exactly like this. You want to go buy a sandwich from a vendor. You have a 20 euro bill. The sandwich costs 14 euros. You go to the vendor and you say, hi, can I have this sandwich for 14 euros? I have a 20 euro bill. And the vendor says, sure, send me your 20 euro bill, which is a 20 euro account. I will take that 20 euro account, break it into two accounts, one worth 14 euros, one worth 6 euros, and I will keep the 14 euro account and send you back an account worth 6 euros. Does that make sense? That's exactly how Bitcoin works. So anytime you send Bitcoin, you're actually sending more Bitcoin than you're intending to send, and you're usually getting back a change account. And so that actually leads to a lot of very interesting forensic opportunities for people looking at the Bitcoin blockchain. For example, if you consider a transaction, let's say that transaction has like 8 decimals, and you're shown one transaction that is like 3 numbers and then 5 decimals. Sorry, let me rephrase this. You're shown 2 amounts of Bitcoin representing 2 of these accounts. One of them is like decimal and then 3 numbers and then 5 zeros. And then another one is a decimal and then a whole bunch of numbers. Which one do you think is the change account, and which one do you think is the actual transaction, the money being spent?
The bigger number?
Probably the bigger number, true, and probably the one with the zeros at the end, because you're probably sending a more specific amount rather than a random amount that would come back as change. So that helps with forensics. Ethereum is different. It works just like your Venmo or Cash App. You simply have an account, you do a transaction. When that transaction happens, Ethereum is a state machine, so the entire state of Ethereum after every transaction actually updates to reflect that new transaction. Okay, and then naturally proof of work versus proof of stake. We're going to skip this in the interest of time. And these smart contracts have led to all sorts of amazing use cases. This is the type of data analysis I want to highlight. This is from a company called Elementus, and I'm just going to skip this here. Yeah. So many of you are probably familiar with initial coin offerings. These are fungible tokens on Ethereum. They're made with smart contracts. What happens is someone sends Ethereum to the smart contract, and to that wallet address that they sent the Ethereum from, they get back this new token from the smart contract. And because all of the data for the smart contract addresses are open and anonymous, they're not really anonymous, but they're open and public, we can actually trace the full amounts of these token raises by looking at the transactions that have been sent into the smart contracts. That's because the smart contracts themselves effectively have addresses that act very similarly to wallet addresses that you have on Bitcoin or Ethereum. And so this was a really, really interesting visualization that Elementus did. They're also able to identify certain patterns in these transactions that might reflect a certain behavior that we might want to discourage or that might not be legal. So here's an example ICO. It's called Car Taxi. This is a Russian ICO. They have this Medium post, and they say, hey, we're a company that has a bunch of tow trucks, and we go onto the it's kind of hilarious. We're a company that has a bunch of tow trucks. We go onto the Trans-Siberian Highway, and we rescue cars that have broken down in Russia, and we need an ICO, so buy our ICO, and it'll really help us do our business. Makes no sense at all. They claim to have 40 customers, and they claim to have raised $7 million through an initial coin offering. Why a company like this would ever need $7 million, I don't know. But if you actually look at the blockchain data and you identify all of the transactions and the relationships between the wallets and the smart contract addresses for the ICOs, these blue circles are all of the third-party wallet addresses that have sent Ethereum to this red circle, which is the first round of the ICO smart contract. We know this wallet here is the car taxi company wallet. Even though it is anonymous, this has to be car taxi because who else would get the Ethereum from the smart contract? It has to be the car taxi wallet. And then this is the second round of the smart contract. These blue circles are also the third-party wallet addresses, and that red circle is, the second round of the ICO. Now, what you see here is a very suspicious transaction pattern. Why is Car Taxi investing in their own ICO? And the reason for this is, it turns out if you parse through the numbers, they only really raised $2 million from third-party investors. That other $5 million was sent to their own smart contracts by their own wallet, and they may have done this to make their token and their raise look more attractive than it actually was. Because you have this element of FOMO. You could say, hey, we raised so much, you should get in on this, and it might encourage investors who would not have otherwise invested to get in. So this is a type of amazing data science you could do because the blockchain data is public. And even though the wallet addresses are anonymous, you could still identify things. For example, we identified the car taxi wallet by knowing that they would get all the money from the car taxi ICO smart contract. And we knew the car taxi ICO smart contract because they tweeted the smart contract address. They told people what the address would be so that they would send the money to it. Okay. All right. This is a Bitcoin Genesis block in raw hex version. You could see that article is referenced there. And something very, very interesting is happening where people are doing something called inscriptions. So they're labeling all of the Bitcoin that is in circulation. For example, you might want a label on all Bitcoin that is the first, that is, owned by a certain wallet in the past. For example, previously owned by the Satoshi wallet. Or you might want a label on all Bitcoin that was mined and came into circulation on the 17th day of a certain month because that's of interest to you. These inscriptions are helping people treat Bitcoin in a new way. They're treating Bitcoin, some specific Bitcoin, as if it's a collectible coin. For example, you guys might collect rare coins, but that's a collecting thing, and this is a new thing on Bitcoin that is happening. Okay, I'm skipping that too. All right, finally, what you guys came here to hear about, a half hour in, Filecoin. And how does this all relate? So, I'm going to tell you a little bit, first of all, about how our internet actually operates. Currently, our internet uses the internet protocol. You've all heard of your IP address, right? So your IP address is a geographic location. It turns out, if you want to organize data on the internet, this is not the best option, because if you were going to tell people where to go retrieve data, you would give them geographic directions. Imagine, like describing street by street where someone should turn to go get a book in a library, including what hallway to turn down, etc. We have a better solution to this, and that's our ISBN system in our libraries. So in the ISBN system, every book has a unique identifier that categorizes it to a genre and a bunch of other characteristics. And so with this ISBN number, if you know the ISBN number for the book, all you have to do is go to the stacks of all the ISBN cards, look up where it would be in the library, and then go retrieve it very easily. On Filecoin and IPFS, I'll talk about both of those, we use something very similar to the ISBN system. It's called content addressing. And with content addressing, every file that gets uploaded is actually hashed with an algorithm that outputs a unique identifier for that file. This is very interesting because if you have the unique identifier for the file, you just need to come to the Filecoin storage and retrieval market, say, hey, I want this file. Who can get it to me the quickest and the fastest? And you can retrieve it from whichever Filecoin storage provider has a copy of that file and is willing to give it to you for the price you're willing to pay. It also leads to many, many amazing features and use cases. So first of all, if, let's say, you take your file and then you come along with an exact copy of that file and you upload it again, the algorithm will output the same exact content ID. But if you make even the slightest change to that file, you're going to get a different content identifier. Turns out this is very important for data provenance. So a group out of Stanford and USC Shoah Foundation called Starling Lab, they actually use this technology to go take pictures and document war crimes in places like Bosnia and Ukraine. And then they submit to the International Criminal Court dossiers with these content-addressed files showing, hey, not only can we show you that this is the original upload of this file, and by the way, there's another cryptographic piece that confirms that the photos are authentic. And then this feature of it, the content addressing, ensures that no one can ever manipulate that data, no one can ever manipulate the evidence, and the International Criminal Court can rely on the dossiers that Starling Lab has submitted. Okay, and then you might say, okay, Robert, this is great. Every file has a unique ID, but on my computer, I like to organize my files into folders. And on Filecoin, we do something very similar. We also organize into something what would be similar to folders, except who's a computer science maybe major in here? Okay. Great. So you may have seen someone talk about graph theory. And in graph theory, we have nodes and edges. So a node in this case would be maybe your folder or your files in the folder. And then your edges would describe the relationship between the folder and those files. So in this case, we have a folder with a directed edge to this file that tells me that this file is in this folder. And so this is how all of the data is organized on Filecoin. And the reason for this, it gives many, many amazing features and the word is slipping from me. But anyway, it's called the directed acyclic graph. And this is how the data is organized. And more or less, all of these nodes and files and all the edges are actually represented all by content addresses. So here's an example of why this is important. Let's say you have the content address for a specific file that you want to retrieve, and it's in a specific folder. Well, you don't need to retrieve everything on the computer to just get that file. You only need to maybe get a subset So it makes it much easier for us to be able to retrieve the information that we're going to get. We could also reduce redundancy in the data structure, which helps us organize this more cleanly. So, excuse me. Sorry, rough week over here. So. All right. So you can see maybe these files here are in both of these folders, but in our data structure, they only need to show up once. And that is the beauty of this graph theory. We call this interplanetary linked data. Now, many people, excuse me. Sorry. It's very embarrassing. I'm trying to get through. We're almost there. All right. And then you guys could all go up to the bar, I promise. Yeah. Okay. Many people come to us at hackathons and say, hey, we use Filecoin. We stored some data on IPFS. IPFS and Filecoin are two separate networks, totally different things. However, they share some commonalities. What do they share? Data on both IPFS and Filecoin are compliant to this interplanetary linked data content identifier data situation. So data looks exactly the same on both IPFS and Filecoin. It's a big difference. Excuse me. All right, maybe we don't put this recording online. Big difference is with IPFS, you have community nodes all around the world that are volunteering to offer to allow you to store with them. And at any time, they could go offline. I'm sorry, guys. Okay, sorry. So, with IPFS, you have community nodes, and at any time, they could go offline because everyone is volunteering to allow you to store that data. With Filecoin, you have specific incentives to ensure that the relationship between you, the person storing the data, and the storage provider, the person with the data center, you have specific incentives to make sure that they store your data over a specific amount of time. So what does that mean? Well, on Filecoin, a client proposes something called the deal. This is a time-limited proposal saying, hey, I have this amount of data. I want to store it for this long. This is how much Filecoin I'm willing to pay for rent to store my data with you over this time. Will you accept this? And the storage provider that has a data center and also acts kind of as a miner will say, yeah, we'll accept it. You pay us this rent over this time. They signal their acceptance by providing a cryptographic proof of replication, showing that they made a replication of the data on their data center. And then every day, every 24 hours, they give another proof called proof of space-time. That is the evidence that data is still there. And when the client that is storing the data gets that evidence, they pay a little more of the rent each day. And if they don't get that proof of space-time, then the storage provider gets Filecoin slashed from their wallet. So there's heavy incentives for the storage provider to stay online and keep your data. Otherwise, they will lose money. So that's the major difference between IPFS and Filecoin. Yeah. And these are the two proof of stakes that Filecoin uses. All right. Now, naturally, like many other blockchains, Filecoin has a virtual machine that allows for smart contracts. What makes the smart contracts interesting on Filecoin is that you have access to the data primitives on Filecoin, and your smart contracts can actually do business logic with storage. So one great use case is perpetual storage. Here's an example of how this would work. You would have a smart contract. You would endow it with a Filecoin endowment that, let's say, you invest it somewhere. And let's say, hypothetically, that investment returns a conservative 8% per year. That smart contract is responsible for checking the storage status of a specific storage deal that you want it to monitor. And the business logic would be something like, hey, if this endowment made more money than it cost me to store this data last year, we can renew this deal this year. If not, we need to find a new storage provider. And so this concept is called perpetual storage. Naturally, those investments are not going to go up forever. There's a lot of holes in this hypothetical, but you could kind of see how smart contracts can be used to ensure that there's not only a financial, let's call it a financial endowment or support for a specific deal that you want to run in perpetuity, but also the smart contracts can check the actual storage deal status and make sure that it's renewed if you want it to be renewed. Yes, okay. Cool. File access control. So naturally, you might want to only allow specific Filecoin wallet addresses to access a specific data set, and you could do that with smart contracts. And the smart contracts would basically say, sign with your private key to prove who you are, and we will send you this data set. Data DAOs, I'm going to skip. But there's all sorts of use cases. This is something I wanted to highlight. It's something we show to our builders at our hackathons, which is I want to do decentralized storage, and I want to do it with Filecoin. How do I make a decision about whether or not I need to use smart contracts in order to go about this? And so there's basically a decision tree here. First, you have to decide whether or not you need programmatic storage at all. Do you need a workflow that requires some business logic around your data? And if the answer is no, no problem. Simple storage, just go store with a tool that will allow you to store on Filecoin. But if you need programmatic storage, there's a lot of very interesting features of Filecoin that influence how you would be able to accomplish this. The first thing that you would decide is whether or not that data is going to be a small amount, being less than 4 gigabytes, or a large amount, being more than 4 gigabytes. What do we mean by this? It turns out the fundamental unit of storage on Filecoin in terms of size is actually the equivalent of 32 gigabytes. We call this a sector. And so a storage provider wants to make the most use of all their sectors, and so they want to mostly accept full sectors in order to accept your data onto their data center. And so there are solutions called aggregators if you have data smaller than 4 gigabytes that will more or less take your data, combine it with the data of other people who also have small data amounts, and fill up a sector with multiple, basically aggregating multiple people's small data. And so you would need to decide whether or not you need to aggregate or not. And then once you make that decision, you can go ahead and build your tool and deploy to Filecoin. Some very interesting projects we saw come out of 2 hackathons we're in the middle of judging. One of them I thought was very interesting, was effectively a Minecraft game built on Filecoin. And although they didn't achieve it yet, in their roadmap is the ability to store the game state on Filecoin. So you can store and reload your game state on a blockchain for the first time thanks to Filecoin's storage capabilities. This is something I haven't seen on other blockchains, and something I think is a compelling example of the specific things the Filecoin storage enables with respect to smart contracts. And of course, there's all sorts of smart contracts going on for the actual Minecraft-like game, where you have a token representing all of the characters in the game and property ownership, etc., etc. Okay, and this maybe gets us back full circle, which is to say storage is only the start. And so Filecoin is kind of the storage layer, and now with Filecoin Virtual Machine, we have what we call computation over state. So these smart contracts allow you to do computation over the state of the blockchain. But now we want to do computation over the actual data that's stored on Filecoin. And why might you want to do that? Well, this is what an AWS job is. It's what your AI, machine learning models, it's how these things are created. You're running jobs, computation jobs over this data. And the project that is working on this is called Bacalao. So I would encourage you all to check this out. It's compute over data for decentralized data storage platforms. What else is going on in Filecoin? The Filecoin Plus notary system is a system of volunteer notaries that actually check the data sets to ensure they're authentic and useful data sets before they're uploaded to Filecoin. And we have Saturn, which is a content delivery network. This is really cool. It's enabling effectively video streaming over a decentralized network for the first time, which is really interesting. And if you were here yesterday for Sarah Tiem's talk on Interplanetary consensus, that's a chain agnostic scaling solution, but naturally it comes out of Protocol Labs. So, people we anticipate will use it to help Filecoin scale. And so with Interplanetary consensus, what you have is a subnet system. And effectively, you could deploy as many subnets that serve as the children to the parent blockchain. These children are effectively their own blockchains with Phil or Filecoin locked from accounts in the main blockchain, used in the child blockchain for whatever it is you need to do, and then settled back when the time is right through a process called checkpointing. I could tell you more about this later upstairs. Okay, based on what I'm hearing outside, I think I'm out of time. Thank you so much for dealing with me as I am kind of in recovery here, but if you'd like to reach out, talk to me about all things Filecoin, come build at a hackathon, we'd love to chat with you. So please take my Telegram, and if you want to get involved with the Filecoin Foundation, reach out to me and I'll send a long list of ways that you could do that. Okay, any questions or?
Yeah, any questions here?
I have a question.
Okay, thank you so much for your talk. I really enjoy it. I was wondering, so permanent storage is like a big issue because monkey brain wants to spam systems. So for Filecoin, it's clear for me that you have like this proof of space time. So basically you are paying rent for the data, but you said something about permanent storage for the application level, like for the VM. Is that working like that or?
The concept is perpetual storage.
Okay.
So I would say perpetual is maybe a step below permanent, where perpetual maybe means a long period of time, almost permanent, without guarantees. Yeah. But it's been demonstrated for sure. So if you want to reach out, I could send you the link to the project that's doing that. It's really interesting.
Oh yeah, like that will be the follow-up, but my main concern was like how to avoid like bloating these kind of systems because I think I need a deeper look. Thank you so much.
Send me a message, I'll send you the link.
Okay, thanks.
Cool. Any other questions? No? So thank you very much. Thank you very much.
Cool.
Just wanted to remind you that we have... Thank you.